8.4 Lesson 1 Trigonometric Substitution. Objective: you'll be able to use trigonometric substitution to solve an integral. Vocabulary: trigonometric substitution. Trigonometric substitution will be used to deal with problems like number 25, where the integrand contains a radical expression. Depending on the form of the radical expression, we will use one of these three trigonometric substitutions. When we use the correct trigonometric substitution for a particular problem, we will change variables, and then when we change variables, we'll be able to eliminate the radical expression. After we find an antiderivative in terms of the new variable, we will refer back to our trigonometric substitution to state our antiderivative in terms of the original variable of integration. Let's look at number 25. We will begin number 25 by deciding which of these three forms our integrand matches. So our integrand is the square root of 16 minus 4x squared. We will rewrite that as the square root of 4 squared minus 2x squared. And in these three forms, or in these three radical expressions, a represents some constant, and u represents some function of x. So if you have the radicand as the square of a constant minus the square of a function of x, you would use the first trigonometric substitution. If you have the radicand as the square of a constant plus the square of a function of x, you would use the second trigonometric substitution. If you have the radicand as the square of a function of x minus the square of a constant, you would use the third trigonometric substitution. For number 25, we will use the first trigonometric substitution because our radicand is the square of a constant, the square of 4, minus the square of a function of x, the square of 2x. Our trig substitution is let u, in our case 2x, be equal to a, in our case 4, times sine theta. We can divide both sides of our equation by 2 and get x is equal to 2 times sine theta. And then we can find dx, the differential of x, by taking the derivative of 2 times sine theta, which will be 2 times cosine theta, and multiply by the differential of theta. Using our trig substitution, we would now like to change variables from x to theta. So we will have the indefinite integral of the square root of 4 squared minus 2x squared. Now we have 2x is 4 times sine theta, so we have minus 4 times sine theta squared, or 4 squared times sine squared theta, times dx, which we know to be 2 times cosine theta d theta. So we have changed variables from x to theta using our trig substitution. We'd like to simplify, and we'd like to try to eliminate the radical expression. One thing that you can see right away is that in the radicand, the two terms have a common factor of 4 squared. So I will factor out 4 squared from each term, and this is what we have. And then in the radicand, I have a product, so I have the square root of a product, and I can write that as a product of square roots. The next step is to replace the 1 minus sine squared theta by using a Pythagorean identity. So we can see that 1 minus sine squared theta can be replaced with cosine squared theta. And of course, the square root of 4 squared is 4, and we have 4 times 2 is 8, and because that is a constant, we can factor it out from the integrand, and we will have 8 times the indefinite integral of the square root of cosine squared theta times cosine theta d theta. When you look at the trigonometric substitution that we're using, it is specified that theta ranges between negative pi over 2 and positive pi over 2. So the terminal side of the angle theta is either in quadrant 1 or quadrant 4, where cosine values are positive. The square root of the square of a positive quantity will be that quantity. So we have the square root of cosine squared will give us cosine theta. So the quantity that I circled in red becomes cosine theta. And when you multiply cosine theta with cosine theta, you'll get cosine squared theta. So that leaves us with 8 times the indefinite integral of cosine squared theta d theta. We must now use a power-reducing formula. Using the power-reducing formula that we see here, the integrand will now become 1 plus cosine of twice this angle, whatever it may be, in our case theta, so twice theta would be 2 theta over 2 d theta. And of course, dividing by 2 is the same as multiplying by 1/2, which is a constant, so you can factor out the 1/2 from the integrand. 8 times 1/2 is 4. And here we can integrate term by term. The antiderivative of 1 with respect to theta is theta, and the antiderivative of cosine theta would be sine theta, so we'll have sine of 2 theta, but because the argument is 2 theta, when you find the derivative of sine of 2 theta, you will actually get 2 times cosine of 2 theta. But you want 1 times cosine of 2 theta, so you multiply by 1/2 to compensate. We have found our antiderivative, but it is in terms of theta. Our original variable of integration is x. So now we have to use our trigonometric substitution to go back to x. Our trigonometric substitution is 2x is equal to 4 times sine theta, or if you divide both sides of the equation by 2, x is equal to 2 times sine theta. We can write that as sine theta is equal to x divided by 2. Using our trig substitution, we will draw a right triangle. Here's the angle theta, and we will use the right triangle definition of the sine function, which tells us that sine of an acute angle theta is the ratio of the length of the opposite side to the length of the hypotenuse. So if we have our acute angle here, then the length of the opposite side must be x, and the length of the hypotenuse must be 2. We will then solve for the length of the adjacent side by using the Pythagorean theorem. So if we label the length of the adjacent side to be a, then we will have a squared plus x squared is equal to 2 squared, which is 4. So a squared is equal to 4 minus x squared. So a is equal to the square root of 4 minus x squared. So we will go ahead and write that in here. A is equal to the square root of 4 minus x squared. This triangle will be key in going back to the original variable of integration x. But to use it, we have to have an angle of theta. Currently, we will deal with theta in a different way than what we're going to do to deal with sine of 2 theta. So let's talk about theta first. How can you write theta in terms of x? You're going to use your trigonometric substitution. So you have sine of theta is equal to x over 2. So if you want to isolate theta, you can take the arc sine of both sides of the equation. So theta is arc sine of x over 2. So now I'm able to write 4 times arc sine of x over 2 plus 1/2 times sine of 2 theta. So this is still something that I need to deal with because I want everything to be in terms of x. Right now, I have 1/2 times sine of 2 theta. So how will I deal with that? First of all, to use our triangle that we have here from our trig substitution, I need to have an angle of 1 theta. Right now, I have an angle of 2 theta. So the first thing that I need to do is use a double angle formula to rewrite sine of 2 theta as 2 times sine theta times cosine theta. When we do that, we will have 1/2 times 2 times sine theta times cosine theta, and of course 1/2 times 2 is 1. So we will just have theta plus sine theta times cosine theta. And to go back to x, we know from our trig substitution that sine theta is x over 2. So we can replace sine theta with x over 2. And we know from our triangle here that we derived from our trig substitution that cosine of the angle theta is the ratio of the length of the adjacent side to the length of the hypotenuse. So cosine of theta is the square root of 4 minus x squared over 2. And of course, you have the mnemonic device SOHCAHTOA to help you remember the right triangle trigonometry definitions of the trig functions sine, cosine, and tangent. But what you can see here is that we have successfully gone back to our original variable of integration x. We are in fact done with the problem, but if you want to clean up the answer a little bit, there is one thing that you can do. You can see that for our second term of the antiderivative, when you multiply, you will have 2 times 2 in the denominator, which will give us 1/4, times x times the square root of 4 minus x squared plus c. And if we choose to distribute this 4 to each of these two terms, then we will have 4 times arc sine of x over 2 plus x times the square root of 4 minus x squared plus our constant of integration, and that would be our final antiderivative in terms of our original variable of integration x. In our lesson today, we looked at an example where we used a trigonometric substitution to help us eliminate the radical expression in the integrand of our problem. Using our trigonometric substitution, we changed variables, and then after that we were able to eliminate the radicand. After that we were able to eliminate the radical expression so that we no longer had a radical expression, and then we were able to integrate. In this particular problem, we had to use a power-reducing formula. We integrated, we obtained an antiderivative in terms of the new variable of integration, theta, and then using our trig substitution and drawing a triangle, we were able to write our antiderivative in terms of the original variable of integration x.